Phonons with Grid Method tutorial. Create a simulation by navigating to the Job Designer page. Then, open the Workflow tab, and choose the Phonon map workflow by selecting it in the list. This workflow can be imported from the bank, if it is not already listed. Now, let us review the component units making up the Phonon calculation workflow. First, navigate to the Important Settings tab of the first subworkflow, for performing a preliminary SCF total energy calculation, and reduce the size of the grid of K points to 6 by 6 by 6, if it is not already so. Then, open the second subworkflow. It generates the grid of Q points over which the Phonon modes will be calculated, for each irreducible representation. The size of this Q grid should be a divisor of the previous K grid, which is why we set it to 2 by 2 by 2. Then, open the only unit of this subworkflow to inspect its contents. Within the Quantum Espresso input script, pay particular attention to the NQ keywords defining the Q points grid. Next, open the third subworkflow in the sequence. It comprises a Python script, whose role is to parse and extract Q points and irreducible representations from the previously generated Quantum Espresso XML data. Each distinct combination of Q point and irreducible representation is added as a separate entry, to what follows. Next, let us inspect also the ensuing map subworkflow. It consists in a mapping function for performing the distributed parallel Phonon calculations, across each pair of Q points and irreducible representations extracted previously. Care should be taken to set the Q grid under the Important Settings of the map subworkflow again to 2 by 2 by 2, as in the previous steps. The list of pairs of Q points and irreducible representations can be inspected under the Data tab of the Map Editor interface. Finally, we take a look at the last Reduce subworkflow. It collects together the results of the previous calculations over each independent pair of Q points and irreducible representations. These combined results are then used to complete the Phonon dispersion and density of states calculation. Here, the size of the Q grid under Important Settings should once again be set to the 2 by 2 by 2 value being considered in the present example. After that, navigate to Compute tab, and set Compute Configuration. Here, we use one node with 8 cores on the OR8Q. Then, set the name for the job. Here, we call it Silicon Phonon Grid Calculation. Next, save the job. It can then be selected and submitted to the compute queue, for execution. The status of the calculation will change from pre-submitted to submitted, and then to active. Please wait until the job has finished running. When the job is finished, open it, to inspect the final results. The Phonon density of states, and the Phonon dispersion plot over the specified path in reciprocal space, can be found towards the bottom of the results page. These final results are in agreement with the published literature, for the case of crystalline silicon. We conclude by opening the Files tab, and inspecting the list of map directories created during the course of the simulation. This completes the present tutorial.